Okay, so today we finally started talking about some of the fluid mechanics principles that we'll be covering through the remainder of the semester, the first of these being hydrostatics. So hydrostatics is, of course, by the structure of the word, you can anticipate fluids that are at rest. The definition of a fluid allows us to immediately conclude that the shear stress, tau, in a hydrostatic fluid is exactly equal to zero. If it weren't, the fluid would move, and it would no longer be a static fluid. So the only force that we really need to concern ourselves with in a hydrostatic fluid are normal forces. Or on a per area basis, that means we need to focus on pressure. So the focus of the rest of the lecture on today was on understanding pressure. And we talked about 4 different characteristics of pressure that helps us to understand what pressure means, how it varies, and how we use it. So first of all, we said that pressure is a scalar. That is, it is a quantity that is potentially a function of space and even time, but it's not a vector quantity. It's like temperature or energy. And we proved that using a finite volume analysis shaped like a wedge. Secondly, we said that in a closed system, pressure changes, delta P, pressure changes are spread or communicated instantaneously. And I'm just going to call it delta P instantaneous. Sorry about the overwriting there. Meaning that a change in pressure at one location in the fluid is immediately communicated throughout the rest of the system. Now, that's an approximation. It actually travels at the speed of sound, but for our purposes, we can assume instantaneous. Finally, we talked about, or third, I should say, we talked about pressure being defined relative to a datum. And the most common datum is, so we could either think of absolute pressure, which is relative to a vacuum, or a gauge pressure, and frequently that gauge pressure is relative to atmospheric pressure. Using gauge pressure is particularly convenient for a lot of the measurements that we're going to be making in the laboratory, or analyses of systems that sit open to the atmosphere around sea level or even higher. Atmospheric pressure is about 100 kilopascals, and so offsetting it to make that zero has mathematical and computational advantages. Finally, the last point that we developed in class was to look at how pressure varies in a fluid. And this analysis was based on a finite cube that we then take the limit of dx, dy, dz going to 0. And we analyzed the force balance on this cube. And I'll just sketch it here for a reminder. Using that force balance, we were able to conclude that the x and y gradients in the fluid, of pressure in the fluid, are both 0. So pressure is constant in the horizontal plane. In the vertical, dp dz is equal to minus rho times g, or minus the specific weight. So together, we can now describe how pressure varies throughout a hydrostatic fluid. Constant in the horizontal plane, increases vertically downwards in an amount proportional to the local density or local weight of the fluid. Okay. Now what we're going to pick up next time is to analyze these variations to describe pressure variations in a fluid that then lead to an understanding of the forces in the fluid.